Hello, welcome to module 8. I think it's going to be week 10 or something, 11. So anyway, so today we're going to learn about, okay, just a moment. Let me check my audio once. All right. So today we're going to learn about Apex 8.3. So I should be a bit more careful here. Which is about the first order differential equation. So what is this? So a first order differential equation looks like the following. Okay, where these px and qx some function in x. So for example, we can consider maybe this equation y prime equals to ey, my beg your pardon, just a moment. So y prime equals to e power y plus 3x. So sorry, that was a wrong example. So one example can be this one, y prime plus negative cosine x y equals to sine x. Or maybe sometimes we can write this equation in a bit convoluted way. So maybe I'm going to write it as y prime e power negative x plus y equals to x squared. See, this is same as nothing but y prime plus y e power x equals to x squared e power x. So as you can identify, this is px. Here, this is px, this is ux, and this is qx, right? So now the question is how to solve these equations. And fortunately, there is a very nice strategies to solve this equation. So how to solve it? Well, so I'm going to do a live example and then also I'll tell you the theory. So suppose your equation is something like this. Y prime equals to px, y, qx. Let's take a typical example. Yeah, maybe you can take this one. Y prime minus 1 over x, y equals to x squared log x. So first of all, step 1, find the integrating factor. Sometimes we call this integrating factor abbreviated as IF. And what is IF? IF is defined to be e power integral px dx, right? So in this case, for example, This is nothing but e power integral negative 1 over x dx. But what is integral negative 1 over x? This is simply e power negative 1 over x dx. So this is 1 over e power, and you can easily see this is nothing but 1 over e power log x, which is nothing but 1 over x, right? Because e power log x is nothing but x. So, right? Okay. Once you find out this integrating factor, what should you do? So step 2. Multiply to the equation, right? So what happens when you do that? So the equation would look like e power integral px dx y prime plus px e power integral px dx y equals to qx e power px dx. Okay. So let's do it for here. So in our example, what happens when I multiply 1 over x with the equation? The equation becomes 1 over x y prime minus 1 over x squared y x log x, right? You are multiplying the entire equation by the integrating factor, which in this situation is 1 over x, as we have computed. Okay, now notice this left hand side is nothing but d dx of y multiplied to the integrating factor. You can very easily check it by chain rule, right? So in the general situation, the left hand side becomes d dx y multiplied to the integrating factor equals to qx multiplied to the integrating factor. Okay. Now, what should you do? The next step, integrate RHS and LHS, right? So if we do that here, what happens? So this becomes y 1 over x becomes integral x log x dx, right? So in this general situation, it becomes y times integrating factor. Right? Makes sense? Now you have to evaluate. So, okay, remember our task was to find out y, right? So that means y is 1 over integrating factor qx integrating factor dx. And that is your solution. So try to do it here. Evaluate the right hand side. So y 1 over x. What is integration of x log x? You have to use by parts. I leave that to you as exercise. But if you do that, you will get this is nothing but half x squared log x. So use by parts. Minus 1/4 x squared plus an integrating constant, right? So that means y half x cubed log x and that's how you solve the first order differential equation. I can do one more problem just for the sake of having more examples. Maybe this one. Xy prime plus 2y equals to x squared minus x plus 1. So first of all, make it look like a first order differential equation. I divided the entire equation by x. So now this is px and this is qx, right? I divided both of the equation by x, right? Now find out the integrating factor. Sorry. So this is e2 1 over x dx. So this is e2 log x. So this is nothing but e log x 2, which is x squared. That means integrating factor is x squared. So multiply x squared to the entire equation. So it becomes, so this is our equation, right? Multiply x squared to the entire equation, right? So the left hand side, as we know, becomes y x squared, and the right hand side becomes x cubed minus x squared plus x. So y times x squared is integral x cubed minus x squared plus x, right? So integrate x power 4 over 4 minus x cubed over 3 plus x squared over 2 plus c, and divide everything by x squared. So x squared over 4 x over 3 plus half plus c, right? As simple as that. Now, sometimes I can give you an initial condition as well. Maybe y of 1 is 1. Then you have to plug in the initial condition to find out the value of c. Y of 1 is 1. That means 1 equals to 1 over 4. Remember, this is y of x, right? So that's how I'm plugging x equals to 1. Right? So find out the value of c. What is this? This is, I think, 7 over 12, I guess. Yeah. So your final answer is? This becomes 7 over 2. That's it. That's all about chapter 8.3. Okay, now let's go to chapter 8.4. So here we're going to talk about real life problems that can be modeled using some differential equation. So essentially there are three kinds of problem. Number one is the kind of problem where the rate of change of the variable, called the variable p, is proportional to itself. So the differential equation is dp dt equals to kp, right? I mean, dp dt is proportional to itself, meaning it is some constant multiplied to k. An example is this guy. I mean, the constant k is 10. What is a typical like scenario? Bacterial growth in a culture, right? So if the bacteria population is denoted by P, then the population model can be the population can be modeled by this differential equation. And what is the solution to this differential equation? So it is always going to be solution will look like y equals to c e power k t. Okay, where c is again some other constant. Similarly, there is one more type of problem which is called Newton's law of cooling. And essentially you keep a hot object and it is slowly becoming cold, and you keep a cold object, it is slowly becoming hot. So that temperature is modeled by this differential equation, this one, where k is again some constant, a is also again some constant, but it is usually the initial temperature of the object. And what is the solution? The solution would look like t equals to a minus c e power negative kt. Okay. And finally, the tank problem, which is very easy to like describe, but usually its solution would look like d equals to some constant minus again some constant e power some constant t. Typically, that is what it looks like. But there is no actually constructive form of the solution for this kind of problem. So let me go through the problems one by one. For that, I'm going to share my screen in the textbook. So first of all, let's look at the bacteria growth problem, right? So look at this problem, for example. So a population of bacteria is growing at rate of proportional to the current population. Initial population is 200 and it grows to 1600 3 hours later. Find the function of the size of population at time t and use it to predict when the population will reach 10,000. So see, you already know that the differential equation would be looking like this, right? dp dt equals to kp. And you also know that the solution would look like c e power k. So all you have to do is to find out the value of c and the value of k for this problem. So you have all these conditions, all these numbers, plug in the values. For example, here, initial population of the bacteria is 200. That means when t is 0, p0 is 200, right? Now p is, or p of t is c e power kt, right? So what is p of 0? Plug in t equals to 0 here. You will get p of 0 is c, right? So c is 200. Makes sense? So the equation, okay, actually I think it is much easier if I like write down. What the hell? Just a moment. All right. Recall that the population is C e power kt, right? Now, the initial population, that is when t is 0, this becomes C e power 0, which is C. And we know that the initial population is given to be 200. So C is 200, meaning, right? So all you have to do is to find out the value of A. Now again, notice that 3 hours later, the population is 1600, right? So P of 3 is 200 e power 3t, meaning 1600 is 200 e power 3t, meaning 8 is e power 3t, meaning t is 1 over 3 log 8, which is nothing but log 2, right? So that means P of t is 200 e power 2 log 2 multiplied to t, right? Now, look at the question. The question says predict when the population size will be 10,000. So that means find t such that pt is 10,000, meaning you have to solve the following equation, which is extremely easy because this is nothing but e power t log 2 is 50, right? So that means t log 2 is log 50, meaning this is t is log 50 over log. Now find this out. So that's it. Newton's law of cooling is exactly similar. I mean, let me just show it to you for the sake of completion. So maybe look at this guy, right? Um, Again, similar kind of problem. Exactly similar kind of problem. There are different conditions for you to find out the value of A, C, and K. Okay. So I suggest you look at this example. Similarly, this is the bacteria growth kind of problem. So look at this entire section. Let me quickly go to number 4. So a tank problem. So for tank problems, first of all, draw a diagram. So there is a tank, right? So this is a 10-liter water tank, has 5 liter salt solution in it. solution in it. Initial concentration of the salt solution is 1 gram per liter, right? So 1 liter of the mixture contains 1 gram salt. Now salt solution in concentration 3 gram per liter flows into the tank. So this is the incoming one. So the concentration is 3 gram per liter and the rate is 2 liter per minute. That means in 1 minute, 2 liter mixture is going into the tank, right? So in 1 minute, 2 liter mixture enters the tank. Question: how much salt does this 2 liter mixture contain? See, 2 liter mixture is entering. So notice that the concentration of the concentration of salt in the incoming mixture is 3 gram per liter. So 1 liter of incoming mixture has 3 gram salt. That's what it means by the word concentration, right? So in 1 minute, 2 liter mixture is coming in, right? So 2 liter of incoming mixture has 3 times 2 gram of salt, which is 6 gram of salt. So in 1 minute, 6 gram salt enters the tank. Right? Okay. And notice that this 1 minute can be measured after t minutes. So our problem should start at this beginning hypothesis. So say t minutes have passed. The tank now contains The tank now contains y t gram salt. So t minutes have passed and the tank now contains y t gram of salt. Why? See, mixture is coming in as well as the mixture is leaving, right? So the amount of salt inside the tank is never constant, right? Also notice that in a minute, 2 liter mixture is coming in. Also 2 liter mixture is going out. So the net volume of mixture in this tank is unchanged, right? The volume of the mixture is unchanged. So initially the tank had 10. Oh, I think they made a mistake. I think they mean 5 gram. I don't know. I think this is 5, right? Yeah. So see, initially the tank had 5 liter of solution, right? Now 2 liter coming in, 2 liter going out in every minute. So what is the net change of the volume of the solution inside the tank? It is still 5, right? So that is one more thing to observe. So notice that the tank always maintains a constant volume of mixture, since in every minute two-liter mixture enters and simultaneously 2 liter leaves. So there is no net change of volume inside the tank. Anyway, now we found out that in every minute, even after t minutes have passed, 6 gram of salt is entering. How much salt is leaving? So now t minutes have passed. 2 liter mixture leaves the tank. How much salt left? See, after t minutes, when the mixture leaves the tank, the salt in this outgoing mixture is same in concentration as the concentration of salt in the tank after t minutes, right? So you have to find out the concentration after t minutes. So total, what is the total volume of mixture? So total volume of mixture in tank after t minutes. What is that? See, we just said that there is no net change of the volume in mixture. This is still 5 liter. Now what is the amount of salt? total amount of salt in the tank after 10 minutes. What is that? That is YT, gram, right? Which is by design, this function records the amount of salt in the tank after 10 minutes, right? So 5-liter mixture has YT gram salt, right? Then the outgoing mixture, which is 2-liter, how much salt does it have? Y/5 times 2 gram of salt. So after T minutes, Y2/5 YT gram salt leave the tank, right? So what is the equation? So change in the amount of salt in the tank after T minutes have passed. What is this? Notice that this is amount of salt entering in 1 minute. So this is in a minute. After T minutes have passed, minus the same thing, minus amount of salt leaving, right? Okay, now this expression is called dy/dt, right? So equation becomes dy/dt. Remember how much salt enters in 1 minute, which is 6 gram, minus how much salt leaves, right? So this is the equation. With the initial condition, y0 is what? 5 times 3. I'm sorry, 1. So what is y0? The amount of salt at the beginning, right? Now, you know the volume of the mixture is 5. The concentration is 1 gram per liter. So the total amount of salt in the beginning is 5. Now solve this. So if you solve this, you should be able to solve it by separation of variables. I leave this to you. So this is dy over 30 minus 2y times 5 equals to dt. If you solve this, it is nothing but y equals to 15 minus 10. So you solve it by separation of variable. That's it. Look at the example. Okay, we are done for this week. See you next week.